okay? And trying to get a grasp on maybe the different formats that we can see polynomials written in, especially today with quadratic functions. There's a couple different formats that, in their own way, are useful. Okay, one format will provide me maybe 2 or 3 things, and a different format might provide me maybe a couple of those same things, but maybe something new as well. Okay, so being able to alter back and forth between one format of a quadratic function and another format will be useful. But we're trying to learn some key characteristics about all polynomials in general, so that regardless of whether it's quadratic or cubic or quartic or quintic or whatever, we can graph them, okay, and have a good understanding of what's going on with them. In this chapter, we will talk about what we refer to as the fundamental theorem of algebra, okay? Which I think is kind of weird because this is your 3rd algebra class, right? And you're just learning then the fundamental theorem. And that kind of allows algebra to do what it does. So it's going to be pretty useful chapter. Some of the stuff, like I said, you know. Some of the stuff we talk about today, you know. So I want to kind of maybe approach it maybe an alternative form, alternative approach than what you've seen in the past. But today it's just dealing with quadratic functions. Okay. We've talked in the past. I've written this for you before. P of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a sub 1 x plus a sub 0. We've seen that before, right? That's just the general way of writing a polynomial, okay? Allowing then that set of a sub n's and n as an exponent ultimately take on infinite forms, okay? A sub n can be any number it wants to be, a sub n minus 1, likewise, a sub n minus 2, likewise, it can be any coefficients that they want to be. The n, though, as exponents, the n and the n minus 1 and the n minus 2, those all have to be positive integers, okay, or 0. Okay, so we want basically our polynomial function to be polynomial. It cannot have variables underneath square roots, underneath cube roots, or anything like that. You can't have fractional exponents, essentially. You don't have division of the variable components, like you don't have like 1 over x, because that'd be rewritten as x to the negative 1, right? You can't have 1 over x squared, because that would be x to the negative 2. And we just said that exponents had to be 0 or positive, right? So it just defines exactly what we want a polynomial to look like. Okay, and these are things like x squared plus 3x plus 6, maybe x to the 5th plus 4x plus 7. Those types of things are polynomials. Okay. Now, what gets people confused is with polynomials, you can't have coefficients that might have roots in them. You can't have coefficients that might have division, like a fraction out front instead of a whole number coefficient. That's fine, but it's the variable part that can't have those things in it. Does that make sense? Okay, so everything in this chapter is going to talk about polynomials. And we'll learn a lot of very, very critical information that gets used repetitively through the next calculus course you take, the next maybe take another calc course after that. It's very useful to know this information about polynomials. Okay, a lot of call them algorithms ultimately in advanced mathematics, and like much more advanced than what we're currently doing, like maybe graduate level courses or 4th year courses, use an understanding of polynomials to help us complete particular algorithms, which is pretty useful. That being said, this is the function that you guys are most familiar with, quadratic function. F of x equals ax squared plus bx plus c. A cannot be 0, because if a was 0, what term goes away? Ax squared, right? And you're left with bx plus c, so you'd be left with a linear term, a linear function. So quadratic has to have an x squared component to it, and that has to be the largest power in the function to be quadratic. Sometimes they call it a degree 2 function, the largest exponent, a lot of times called degrees. So we call that a second degree function or a second degree polynomial, more specifically called a quadratic. Is that all right? Is that new? Hope not. Okay. If we go on, what we're going to do, we're going to try to take like ax squared plus bx plus c. I'm just going to enlarge this real quick so we can see a little better. But there's that's what we call like quadratic form. What I don't like about this section, and it's kind of what we've as mathematicians have kind of developed because we weren't consistent at some point. Some people call it I guess the right way to call this is quadratic form. Some people call this standard form. Some people call it general form. And we're going to change it into some other form. And some people use the same terminology. So the other form that we talk about here in a little bit, our textbook actually calls standard form, where other textbooks call this standard form. Does that kind of make sense? So there's a kind of a misuse of maybe what standard means. I like to call this standard form, but your textbook just calls it like quadratic form. So you might hear me try to make sure that I say it correctly, just because I've been ingrained to call it standard form. But I think your textbook's going to call it quadratic form. And then the other format that we come up with here in a little bit, they're going to call standard form, which I think is better referred to as vertex form, because it tells you the vertex. But nonetheless, we get some information from this format. Okay, this format tells me a lot if I know that A coefficient. Okay, that A coefficient, if that's positive, okay, I don't care how big it is. Hopefully, we know that the bigger that number is, it's more of a vertical stretch for our function. Okay, but the way it's written, that A would not necessarily be that we're stretching by that A. It might not be a stretch of 2 or 3 or 4 if that A was there. And we'll talk about that as we kind of move through the procedures here. But A, if it's positive, your graph is going to look like that parabola. Okay, so that's A being greater than 0, A being positive. What was do you guys remember from Algebra 2 what that orientation is called for a parabola? Starts with a C. Ever remember hearing this phrase? Concave up. Okay, it's a huge term that we need to know. Concave up basically means your parabola would hold water, right? Okay. So if that's concave up, what do you think that's going to be called? Concave down. And what do you think A has to be in order for that to happen? Yeah, A is less than 0. A is negative. Okay, so that's concave down. All right. As we go through this course in calculus, it's going to be very important for us to be able to recognize concavity for functions. Some functions change concavity. Okay, if you think we'll get there eventually, but kind of seeing where this leads to. If I look at this cubic, does that thing change concavity? Over here, does it look like it's concave down? And over here, does it look like it's concave up? Okay. So as we progress through this course and the next course, it's going to be important for us to be able to find that point right there. Calculus does a lot to find that point for us. And we start dealing with whether it's concave up, concave down in those intervals. We start talking about the first derivative test and the second derivative test in calculus to do those things a lot easier for us than the way we'll do it in this course. Okay. Those are pretty useful information, or is pretty useful information. Okay. Now, if I'm thinking about this function and this b term, right now maybe not a whole lot of information gained from that b term, but this c term here gives me a lot of information because if x is 0, okay, when x is 0, I'm talking about what kind of intercept? A y-intercept. When x is 0, okay, so if x is 0, we would have that term go to 0, right? We'd have that term go to 0, and we would be left with c, correct? Okay, so f of 0, when x is 0, we're left with a y value that is c. So that c term right there, what's really nice about it is that provides me my y-intercept. go back to what you talked, and this is true for any polynomial, not just quadratics. If there's a constant term at the end, go back to a line. If I had the line y equals 2x plus 5, what's that plus 5 tell me? That was my b term, right? Y equals mx plus b, that was the y-intercept, correct? Okay. Well, for quadratics, because we got one more term, we have to use one more letter, so we call it c term. Okay. If I go to a third degree polynomial, there'll be a plus d at the end. Okay. And that d will be my y-intercept. Does that make sense? The non-variable part ends up being my y-intercept. That's the only thing that doesn't disappear when x is 0, right? Okay. So that is really nice to be able to provide me with some criteria for my graph. So there I've got one, looking at it in what we call a quadratic form there, or some books call it general form, whatever. When we look at it that way, we get two things: concave up or concave down, and we'll get our y-intercept. Okay. Now, looking at it in an alternative form, we might get the same two pieces of information, but an alternative form also provides us some extra stuff, okay, which is pretty useful. To be honest with you, I don't like this form. I think it's pretty useless. Okay. There might be applications for it later on, but in general, for a quadratic, that's kind of ugly. Okay, but we can gain some small pieces of information from it. All right. So this is what we want to do. You guys know that if I take the quadratic form, okay, and I let a be 1, and I let c be 0, and I let b be 0, I get f of x or y equals x squared, right? And you know what that looks like. You know what that parent function is. Vertex is 0, 0, has a point on 1, 1, a point on 2, 4, negative 1, 1, and negative 2, 4. And you can repeat that process to find as many points as you need. So you know what x squared looks like. Okay? Every function that is quadratic is going to behave the same way, but maybe somehow altered using basically our transformations. Okay? All right, this is what we call standard form. Like I said, some textbooks don't call it standard form. They call what we just did standard form. I prefer to call this vertex form, okay, because it is very explicit in what your vertex should be when it's in this format. I don't know, because at the beginning of the year I had a choice to choose textbooks. I could have either used the one we're using or one called OpenStax. This one I think is better in regards to the material and the content and the way they present it. So I chose this one. I have to go look at OpenStax to see how they refer to this form, where they call it vertex or standard. And the reason I'm telling you this is because the lead instructor at Rhodes uses the OpenStax textbooks. They use different textbooks than we do. Same material, but different textbooks. Are you looking at that? Oh, I'm sorry. Can you imagine me that small and somebody just comes swats you? If I had, so you get the test on whenever I give you the test for this stuff, and there'll be a question on there about this. I don't know whether they'll use standard form or vertex form. Now, a week out, I'll know. Yeah, or 2 weeks out, I'll know. And I'll relay that information to you. But the idea is there's really only two formats. There's either the long ax squared plus bx plus c, the polynomial kind of format, or there's this one. Okay? So if they give you this one, and they say change the form, they want you to go into that one. Okay? And if they give you this first one, we start off with here, and they say change the form, they want you to get down to this bottom. Does that make sense? You only have two formats. So that one there is a little bit better. F of x equals ax squared plus bx plus c can be transformed pretty easily into f of x equals a times some quantity x minus h power squared plus k. Okay? Where ultimately your a, b, and c kind of reorganize themselves, okay, to become a, h, and k down here. Okay? Again, looking at this, okay, the function here allows us to look at that a term, and the a term, again, tells us the concavity. If it's positive, it's concave up. If it's negative, it's concave down. Okay, so you're seeing that represented in the picture over here, right there, and right there. Okay. Something that people struggle with, I think, is instead of them saying the word positive, it says a greater than 0, and we have to interpret that means positive. Okay. What I like about this format is if we think back to what we did on the last test, if I had something that looked like, let's see here, looked like f of x. I think on the test it was -1. What did that -1 do to my parabola or my function? Moved it right 1 unit. Okay. So, and if it was minus a -1, it would become +1 and move it which direction? Left 1, right? So this h here tells me where my vertex of my parabola has moved either left or right. Does that make sense? If it ends up like being x -3, it's moved right 3 units, correct? If it becomes x +3, it got moved left 3 units. So that tells me the x value ultimately of my vertex of my parabola. Okay. And then, like say I had like +5 over here on the test last time. What did that +5 do to the graph? Moved it up 5, right? Okay. Well, that's what we're seeing right here with the +k. That +k tells me that my vertex has got moved up k units or down k units. We put -h and +k there, but h and k could be respectively both positive or both negative or one of each. Okay, so it doesn't really matter. But our vertex of our parabola, our parent function is located at 0, 0. Okay, but if I want to move away from 0, 0, the vertex now becomes h comma k, h being the horizontal displacement, and k being that vertical displacement. Okay, so you see here that if we move h to the right and up k, okay, 0, 0 would have been there, right? So we got that parent function for my parabola. Move to the right h, move up k. Okay, same thing over here. Move right h, move up k, and it gives me that vertex. Does that kind of make sense? Concave down, concave up is also something we want to pay attention to. So I want to talk about how we go from f of x equals ax squared plus bx plus c down to f of x equals a times the quantity x minus h squared plus k. And you've already done it. We've done it a lot. Okay? And it becomes a technique that is very useful for the rest of your math careers. Completing the square is going to be something that's very, very useful for all things that you do mathematically from here on out. Okay? So we've done this. We've done this a lot this year. This is express f in standard form, or like I prefer to call it, vertex form. Okay. Hopefully you recognize now why we call it vertex form. That's the key component, the key information that you get from that. I'm going to delete this because we'll get to it, but I want to do it by hand first. Okay. But then we'll find all these components of this function by hand and then see what our calculator might help us kind of do more efficiently. It says let f of x be 2x squared minus 12x plus 13. It says express f in vertex form. So we need to transpose this into a different format. And there's a general procedure for that. And like I said, it's completing the square. And if you remember completing the square, I'm going to write this one. I'm going to go 2x squared minus 12x plus 13. Just for some reason, I think it's because when I was in high school, this is the way we did it, so it's just what I'm trained to do. I always put the f of x when I complete the square, I always put it on the right. But if you remember with completing the square, the number one thing we want to do, I guess it's really two things. We want to get that number there, that 2 out front, whatever that coefficient is, we call that the a coefficient. We want that to become what? We want that to become 1. Okay? And the next thing we want to do is make sure that this 13, the constant portion, ends up on the other side of the equal sign, right? Okay? So you can do all that stuff at once. Okay? The steps are independent. You can move the 13 over first and then divide everything by 2. You can divide everything by 2 and then move the 13 halves over. It doesn't matter. But I'm going to do it all at once. So I'm going to get, eventually, x squared minus 6x. I'm going to leave a gap here, a little, because I'm going to put a term in there in a moment. So leave a little space there for yourself. And then I'm going to have f of x minus 13. Okay? But remember, I divided everything by 2, right? So when I divided the 2, x squared, and the 12x on the left-hand side, those went down to whole numbers. The 13 is not divisible by 2, and neither is the f of x, so we just write it out. Is that doable? If you want to write that right-hand side as f of x minus 13 all over 2, that's fine. It doesn't matter. It's the same answer regardless. So now we got to set up to complete the square. And if you complete the square, the first thing we do is we look at this number here, right? We look at that 6, and we take half of it, and then do all of that half square. So half of that's 3, square is 9, right? So add a 9 to the left-hand side. What do I have to do to the right-hand side? Add 9, okay? Now just being kind of intelligent about this, I'm going to add 9, and I've already got a denominator over here of 2. Probably better to add it this way, wouldn't it? 18 over 2 instead of 9. Okay. Still 9, though, right? All right, so why we did that is because now the left-hand side, if you remember the terminology, that's a perfect trinomial. Okay? Meaning that it can be rewritten as a binomial squared. And that binomial squared there's always going to be an x there. Okay. Now, what's nice about this, okay, is that we always put that sign right there, in the middle, and that's always half of what that term was. Half of that term. Okay. So half of that was 3, right? Now, if you think about this, I don't want to spend a whole lot of time talking about this, but if you remember anything about coming up with the quadratic formula, this term right here, we divided everything by a up here, right? Okay? So this 6 is actually the b term over a. Does that kind of make sense? That's what that 6 right there is, the b term divided by a. But this 3 here is now half that, correct? So if I multiply that by 1/2, I get something that looks like this. B over 2a. Okay? I'm going to come back to that b over 2a here in a moment. But that becomes very, very, very important for us to kind of expedite the process and make things a little bit more efficient for us when we want to change things into vertex form. From quadratic form to vertex form. So I write this perfect trinomial as x minus 3 squared. Now the right-hand side becomes, f of x over 2 plus 5 over 2. All right? Okay. Now once you do that, once you've essentially completed the square, you've got everything that you need now. Now we just need to go back and solve for f of x. We need to get that thing all by itself again. So by doing that, I'm going to come up here. Sorry, I'm running out of room here. But I'm going to come up there, and I'm going to rewrite this. So doesn't matter the order. You can multiply everything by 2 to get rid of the fractions first, or you can move the 5 halves over. Doesn't matter. But you're going to end up with x minus 3 squared. I'm going to move the 5 halves over. Minus 5 halves is equal to f of x over 2, right? I want to solve for f of x. So if I want to solve for f of x, what do I need to multiply everything by? 2. So it becomes 2 x minus 3 squared minus 5. And that is your new f of x. Okay. Now, can I erase this word? Everybody kind of caught up to that? Now, what is nice about that, if you go ahead and, I think there's got a built-in check here. If you go ahead and FOIL that out, multiply by 2, subtract 5, you will get back to 2x squared minus 12x plus 13. Does that make sense? So if you think you've correctly transformed from one format to another format, when you're done, take your final format, in this case that vertex form, and just do all those, just expand it. Do all the operations that are there, and you should get back to 2x squared minus 12x plus 13. Okay? If you didn't, you did something wrong throughout that process of completing the square. Okay? But what is nice about that now is that we see our parent function. Our parent function is something squared, right? Okay, so in our mind right now, we're thinking parabola, right? And we're thinking x squared. We're thinking this picture right here. Let's see here. We're thinking that because of the power of 2 in there. It's the largest degree, right? Okay. What does that minus 3 on the x do to that curve? Moves it right 3. So 1, 2, 3. And now what does that minus 5 do to that curve? Moves everything down 5. So 1, 2, 3, 4, 5. And now we get that curve, right? Or that gets that vertex. So 0, 0 now goes to 3, negative 5. Still concave up, that's a positive 2, right? Concave up. Okay. Now there's some other points on here that we didn't really gain from looking at it in vertex form. Okay. That 2 is a vertical stretch, right? It's going to make all my y values twice as big as what they were on basically the x squared function. But if I look at that format, if I look at 2 times x minus 3 squared minus 5 equals fx, does that format provide me a y-intercept as nice as the original f of x did? No. Okay, if I look at f of x equals 2x squared minus 12x plus 13, the real nice thing about that format is that when x is 0, this thing wipes away, right? This thing wipes away, and you're left with just 13, correct? So this point right here, 0, 13, correct? Okay, now, if I were to look at it in this form, 15, 5. If I look at it in that form, is that 13 real obvious? No, you got to do some work there, right? You got to plug in 0, get negative 3 there inside the parentheses, square that, get 9, double that, get 18, subtract 5, and there's my 13, right? Okay? So hopefully you see the benefit of having both these functions, right, in both formats. Ultimately, this original format, okay, quadratic format, the best thing it provides you is the y-intercept. The best thing this format provides you is the vertex. Okay, they both provide the same concavity. But then they ask you to find the y-intercepts and the x-intercepts. So we found the y-intercept. Now we find the x-intercepts. Okay, you can do this either way you want to. You can go back to the original function, and you can complete do the quadratic formula, right? Which is completing the square, correct? Same thing. And we've already completed the square, right? So I'm going to use this thing here to find my x-intercepts. What coordinate is 0 when you're talking about an x-intercept? The y, right? So can I solve that equation? Can you add 5 to both sides? And get 2 times the quantity x minus 3 squared. Can you divide both sides by 2 now? And you get 5 halves equals the quantity x minus 3 squared. Now what could you do? Square root both sides. So you get plus or minus square root of 5 halves equals x minus 3, right? So now would x equal 3 plus or minus square root of 5 halves? Does that make sense? Okay. Now, they're not really nice cute numbers. If you think about 2x squared minus 12x plus 13, that thing's not going to factor using really nice techniques like the product and sum technique or the A times C method or factor by group or anything like that. You're going to have to use quadratic formula. And if you use quadratic formula, you will get down to simplified form of 3 plus or minus radical 5 halves. Okay? So there's your x-intercepts. Is that doable? Okay? So you're getting a lot of information from these two formats. Now we want to sketch the graph. Okay? Well, sketching that graph, got to come over to this and do it. All right, so if I take, what was it, 3, here. 3 plus square root of 5/2 gives me that number, and 3 minus that gives me that number. So those are my x-intercepts. Okay? I'm going 4.6 and 1.4. Okay? So 4.6. So 1, 2, 3, 4. All right, so 4.6 maybe about right there. 1.4 maybe about right there. Okay. My vertex was at 3, 5, 3, -5, right? 1, 2, 3, 4, 5. What's nice about that is that you see that this 3 here is that symmetric with respect to that intercept and that intercept. Does that make sense? And that should be for a parabola. That's a feature of all parabolas. All right, so I've got those, that vertex, those x-intercepts, but I've also got, and my scale's messed up, but I've also got the y-intercept of 13 up here, right? So now I could connect those. It's a terrible job with this thing. But now we get a rough sketch of our parabola, right? Okay. Kind of hard to draw with that tablet back here. Now they ask for a domain. Okay, they ask for a domain. What is the domain? What kind of polynomial, or what kind of function is it? It's quadratic, but quadratic is from the family of, starts with a P, polynomials. And all polynomials have domains that are all real numbers, negative infinity, positive infinity. Okay? The range, this is where we messed up on the test. When I do the range, remember we're taking a horizontal line at the bottom of our curve, and we start sliding that thing up. Okay? And the first y value that I encounter starts my range. Okay? So what would be the first y value that I encounter? Yeah, -5. Now I'm going to include that. And now as I move that horizontal bar up, what's the last y value I would encounter? Infinity. Okay? A lot of people on the test were taking that horizontal bar, starting at the top, and dragging it through the bottom of the curve. Does that make sense? And that, if you do it that way, you still get infinity, and you still get -5, but what happens with these two numbers? Yeah, they're backwards. Okay, so that means your number line is ultimately backwards. Okay, is that doable? Okay, so they're going to ask us a lot of stuff that's consistent with what we've been doing, right? We've been doing domain, we've been doing range, we understand y-intercept, x-intercepts. Now it's got a conglomeration of all those things inside one problem. Now, let's talk about how our calculator might be able to benefit us somehow. Okay, so again, it might be nice to have your calculator so you can go through this. It's not an extremely difficult process, all right, but it will save you maybe some steps in completing the square. Okay, we're still gonna have to do some stuff by hand here, but I think the stuff we have to do by hand here is a lot easier than the completing the square process by hand. First thing I'm going to do, I'm going to y equals, and I'm going to type in that function. Okay, so y equals, and I look at that function. Okay. The only drawback right now, I guess, of using your calculator now, I use the old TI-83s, A4s, so I don't know if the new ones, if it's changed or not. But the only drawback is, like, if I go through this work, I might get my vertex. It might tell me like 0.33333333. So what do I have to interpret that as? 1/3. There might be times, now I know you probably don't have like 5/12 committed to memory or 5/31 committed to memory as a fraction, right? So there might be times where we want our answer to have fractions in it, but the calculator provides decimals. You might have to do a little converting, but it's still something that can be useful to us. Okay, so I'm going to graph that. So I go to graph, gives me my nice little parabola there. Okay, I shouldn't have to change the window at all. If your window doesn't look like that, just go to standard, go to zoom 6, and you'll get to that window. Now I want to take my function that was in quadratic form, and I want to put it in vertex form, right? So my calculator has the ability to tell me what that vertex is. Okay? If I go to second calc, okay, which is the, it's the trace button, right? Second calc, and it gets me here. Now, if I look through that, it doesn't say anything about vertex, does it? But it says what? Minimum, correct? And for the function that I just, that's why I wanted to graph it first, because I wanted to recognize we have a minimum and maximum. We should have known that by looking at the A term of positive 2. We should have a minimum. But I want to go down to minimum. All right? Hit enter. And now it asks me to find a left bound. So I think my vertex is about right there, correct? So when it says left bound, you just want to be to the left of it. And hit enter. And then when it says right bound, you just want to be to the right of it. Hit enter. So what we've done is we've told the calculator, I think it's always important maybe to understand what your calculator is doing. We just told our calculator to go ahead and look at these x values. Look at those red x values. And plug them into our function. Okay? So it's taking the infinite number of red x values out of that little restricted domain. And it's going to plug it into our function. And it's going to spit back to us the minimum that calculation produces. Does that make sense? Okay, and that minimum then should be that y value right there, right? And it'll come back as a repair. So when it says yes, we're going to want it to do that. So we hit enter. And I get that. Okay. Now, some of yours probably gave back a 3, right? Mine gives back usually a 2.999999. Gives me something very close. If yours does that, I've got a lot of things kind of working in the background on my computer right now, so I don't have a lot of memory, RAM, and that could be a reason why it's not getting me 3 back. Does that make sense? But I need to interpret that as a 3. Okay? And then this is -5. So that's my vertex, right? 3, -5. So now going back and I'll put something in vertex form. Well, f of x in vertex form is a x minus h squared plus k. Okay, where h and k are your vertex, and you just found h to be 3 and k to be -5, right? Plug those things in. We have a x minus 3 squared. K is now plus a -5. That's right, as -5. And now think about it. Once you've written that, think about, did that do everything I wanted to do? Okay, that x minus 3. Minus 3 to an x value moves it to the right, correct? Did that graph mimic that? Yeah, it was moved to the right 3 units. And that -5 moves my graph down 5 units, so my graph mimicked that. Okay? So I now know that that is correct. Okay? But here's the thing. If I were to FOIL this thing out, okay, I don't get back to this. I don't get back to f of x equals 2x squared minus 12x plus 13. Okay? Because I'm missing that coefficient of 2 right now, right, that we needed. Now, you can't just say I'm going to, because this was a 2 up here, okay, then I'm going to make this a 2. Okay, I think that, I mean, logically, maybe you can think that would work. What was that all about? I don't want that to do that. Control Z. Did you guys see that? You see what happened there with my writing? Something. I don't know how to do that. All right, so we get that. So that's what we got. I don't want to just take the 2 out of f of x and plug it in for a, because later on, this process is going to be useful for us. So I want to teach you here. We need to find this a term. Okay? And the only way I can find that a term, because there's an infinite number of functions that have the vertex at 3, -5. Does that make sense? Okay? If I look at, let's see here. Okay, so if I look at this function here, okay, that is a function of having vertex at x minus 3, so -3, so I'll move the right 3 units and then down 5, so I get the vertex 3, 5, right? But as I change that A value, we start to see that those are different graphs, right? Okay, so that A value could be anything. And right now we don't know what it is for our particular problem, but there's an infinite number of graphs, either concave up or concave down, that go through the vertex of 3, negative 5. Does that make sense, everybody? So we've got really, what we've done here so far is we have the general equation for that parabola that goes through that vertex. We want a specific one. We want the one that when I FOIL everything out, I get a 2 out front. Okay, that's just how we do this. We need another point on this curve. Okay, and there's a bunch of different ways you can do this, but don't I know from here if x was 0, y is what? 13. That's a really key, useful point. Okay, that's an x value, and 13 is an f of x value, right? Can I substitute down here now and say f of x is 13? I got my a still because that's what I'm trying to find, but x just became 0, right? Because when I have f of x equals a times x minus 3 squared minus 5, I really have 3 variables there. I have f of x, or a y, I have an a, and I have an x, right? Well, if I know 2 of those, I can always solve for the third one. So I know those 2, I plug them in, okay? So now I get 13, okay? Negative 3 squared is 9, right? So 9a minus 5, what can I do with that 5? So we get 9a is equal to 18, so what's a? 2. So now I come up here where I had this red a, and I now know for certain that it's a 2. And if I go ahead and I FOIL that out, expand that, f of x equals 2 times x minus 3 squared minus 5, I will get back to 2x squared minus 12x plus 13. So we've transformed it into vertex 1. Okay? And that's just an alternative option for you. You don't have to use that technique. If you prefer completing the square and you want to do that every time, do that. Okay? But I think as you go through the course and we start doing other things, that will be a nice tool to have that'll allow you to quicken the process sometimes. Does that make sense? Okay. We'll come back. We talked about that b over 2a. Okay. It was actually opposite b over 2a. We talked about that earlier. Okay. Well, where's it at? That number right there is the opposite of b over 2a. If you take that number, opposite of it, be 12, right? Okay. Divided by 2a. 2a would be 4. What's 12 divided by 4? Is that 3, right? Okay. And that's the component then for the vertex. Is that doable for everybody? And if I know that vertex, if I know that x value for my vertex, can I plug that 3 right here? Okay, what's 3 squared? 9 times 2? 18 minus 36. What's 18 minus 36? Negative 18 plus 13? Negative 5, right? Okay. So what ends up being something we'll talk about tomorrow is that opposite of b over 2a. That thing is so much more important than anything we did today. But when we talk about tomorrow, this is how we came about it. Does that kind of make sense? This is the procedure that got us there. We'll continue this up tomorrow. I have posted, or I will post, a homework that you guys can start on. But we'll get to talking about that opposite of b over 2a tomorrow.